Joel, thank you. I work with good people. You just heard from one of the best. Thank you very much. I also want to thank, there are two things going on here. One is what I'm going to say tonight, and another is a book. And you're not going to hear much about the book except the fact that there's some parallel between what's in the book and what I'm going to present tonight. But I have to commend Emily Cook and Andrea Velasquez for the propaganda, I'll call it, to suggest that a talk about quantum mechanics could be a good thing. We'll find out. I'm also electronically connected to things that should make me audible. If I'm not heard by somebody in the room who would actually like to hear me, you could make a commotion. I'll try to improve on that. Two things I would like to do is one to do with the book, another to do with the kitty cat. And having acknowledged the folks who've helped with this evening, I also want to acknowledge the people that made the book possible. Len, who is subjecting herself to this stuff again, had a very different notion of what my retirement would look like. The idea of an elderly chap in the back room huddled over a laptop for about 12 months wasn't in her picture of what that was, but that's what it turned out to be. And she still is there, and she is still here. Thank you. Three people read most of what's in the book, read it very carefully, commented on it, made it better, read it again, made it better again. And they are Paul Burdon, formerly of our math department, and Dan and Irina Mazalu, currently of our physics and engineering department. Without them, the book would be much worse, but it is not their fault. What I want to do is to explain two things. What is discrete about discrete quantum mechanics, why that title, and the other, who or what is Schrodinger's cat. And I think if I succeed at one of those, I'll go home happy. And I do plan to go home before the Virginia Tech game starts, before the Cubs game starts, and maybe before most of you leave. This is going to require talking quite a bit about the history of quantum mechanics, and it has to start with the person that really initiated the idea. Max Planck. He presented a paper in December of the year 1900. And there was this end of the century idea among physicists, and it happened again at the end of the 20th century, of, don't worry, we got this. There's so much we know about nature through physics that what's left is details. There's nothing new to be discovered, and that's what the majority opinion was at the end of the 19th century. Two reasons for that belief. One is Isaac Newton, the middle of the 17th century, who had presented a theory of how particles behave, how they interact, how they move. A very predictable, a very deterministic theory where if you know enough about now, you can predict the future with perfect precision. Well, the problem, of course, is knowing enough about now, but that was the idea of Newton. Then, only about 50 years earlier, in the 1850s, J.C. Maxwell developed a theory of electricity and magnetism, how those two phenomena were in fact one phenomena, two aspects of one phenomena, and helped describe radiation, light, infrared, ultraviolet, all manner of electromagnetic radiation. With those two things in hand, there was good reason to believe, we got this. There was a problem, however, and the problem had been about 10 years old as of the year 1900, having to do with this, what's called black body radiation. If you stick a piece of metal in a fire and it heats up, it'll begin to glow. And the hotter it gets, the more light comes off, the greater the glow, and also the color changes, the mix of colors that come off of a glowing body. That's called black body radiation, and combination of Maxwell and Newton were not enough to explain what was going on. There's some very confounding ideas. And at this December 1900 meeting, Max Planck proposed that the glow was not continuous. It was not kind of a fluid of energy, but it was lumpy. If you assume that what comes off of that glowing piece of steel in your fireplace is not continuous radiation, but photons, new idea that he presented, energetic particles, you could explain both the color and intensity of radiation that comes off of a glowing hot body. First quantum explanation, Max Planck, 1900, his Nobel Prize, and most everybody I talk about today will be a Nobel Prize winner in physics. He won the Nobel Prize in 1918 for this work. So we go down the gallery to the next portrait, and it's Erwin Schrodinger. Schrodinger, 25 years later, looked back at the kind of collection of work that was done in both experiment and theory for quantum phenomena, things that no longer agreed with what Newton would have or with what Maxwell would have, but were unusual. And these experiments and the theoretical explanations of those particular experiments formed a body of work that was not particularly coherent. What Schrodinger did was to produce a coherent theory that explained all of these things. And his theory was a wave theory. It was based on the notion that quantum things, at this point it was thought maybe electrons, maybe atoms, maybe nuclei, not real sure about other things. We'll find out that cats work too. Behave like waves. And this picture represents, and you can imagine it, several things, but if you imagine an overhead view of some very regular ocean waves coming in towards a seawall where there are two narrow gaps. And what happens when the waves hit those gaps is that some of the wave energy passes through each gap. But what it doesn't do is send a little gap-shaped bit of wave in a straight line. What happens to the energy that comes through here is it spreads out. And that phenomenon is called diffraction. Waves diffract. Water waves diffract. Sound waves diffract. Electromagnetic waves, visible light, diffracts. The other thing you can see going on here is that the wave energy that came through this gap and this gap overlap in a certain region, and strange stuff is going on in that region, because with these two sources of waves, of up and down undulations, there are regions where the up undulation of one source coincides with the down undulation of the other source, essentially canceling each other out. So all this up and down over here with an up and down over here turns into nothing. And these dark areas in that region correspond to that kind of destructive interference. As far as water waves concerned, if you were standing in the water here, you would feel no wave action or very minimal wave action. But to your left and right are regions that are colored in that overlap region where the waves are higher than the single waves that came through either of the gaps. Constructive interference. Waves do that. Particles don't do that. You don't throw two baseballs together and find no baseballs. But de Broglie proposed something different. This is Louis de Broglie, finishing his dissertation at the University of Paris, 1924, and proposed, why don't we pretend electrons do this? Electrons, baseballs, hard particles. Let's assume they diffract and they interfere, not only with each other, but interfere with themselves. Crazy idea. The faculty at the University of Paris was not crazy about the idea. They were all trained classical physicists. And they sent this dissertation to Berlin, which is where Einstein was at the time. And he read it, and he said, it's a crazy idea, but it's consistent. So give the boy his degree, send him away. Okay. So they did. 1924, he was sent on his way. 3 years later, electrons were experimentally seen to interfere and diffract. 3 years after that, de Broglie had his Nobel Prize. Okay, so Albert got it right. So, yeah, Emily's cat had to leave this evening, so we were using a different cat. Those who know about Erwin Schrodinger know about Schrodinger's cat. Very few people who don't know about one know anything about the other. But if you go and Google the term Schrodinger's cat, you get about 500,000 hits. So it's a very popular notion. Seldom is this cat given a name. I propose to call it Fluffy. So we'll talk a lot tonight about Schrodinger's cat, about Fluffy. We'll see a lot of him, but not immediately. So we move down the gallery to another chap, Werner Heisenberg. Schrodinger is Austrian, Heisenberg German. He also looked back at this 25 years of work from 1900 until about 1925 and said, I can create an encompassing theory of all this work too, and it was profoundly different than what Schrodinger had to do. It was not waves. It was not continuous behavior of things. It was discrete. Thus, the name on the book. It turns out, almost by coincidence, that the various things I did in my research career, which were quite unrelated to one another, all seemed to be physics that was best explained using Heisenberg's idea rather than Schrödinger's idea. And so when I sat down to get something off my chest, it happened to be the things I knew best, and that's why I wrote about this. But Heisenberg published his theory in 1925, the end of 1925. Schrödinger, I think, was January 1926. So these guys were totally independent of one another and both claiming to have encompassed a quarter century of quantum science. Now, the discrete nature of what Heisenberg had to do relates to two things. If you remember when I mentioned Planck, I said this radiation coming off of a hot object when it glows was lumpy. The photon notion of light being made up of little particles. That's one of the discrete pieces that Heisenberg jumped on. The other was the so-called Bohr model of the atom. This was 1913. Niels Bohr was working in the Cavendish lab in England and studying the nucleus, and came up with this notion that explained the experimental results they were getting, that the atomic nucleus is very dense and actually much smaller than this picture would represent, very dense core carrying most of the mass of an atom, and electrons kind of buzzed around outside in discrete orbits, not anywhere they wanted to. It wasn't planetary in the sense that we still believe that if the Earth were placed 10% more distant from the Sun, it'd be happy there. If it had the right speed, it could orbit. There's no particular groove that the planets have to sit in the solar system. But according to Bohr's model, there were grooves for electrons. They couldn't be elsewhere. If you tried to move this little guy that way, it wouldn't move until you pushed hard enough to have it jump to the next level. So one of the immediate successes of what Heisenberg did was to explain this phenomena in a mathematical way. So now we go back to Heisenberg and Heisenberg's dog. Heisenberg's dog, I was stunned. I Googled Heisenberg's dog, and I got nearly as many hits on that phrase as I did on Schrodinger's cat. And it turns out that some fairly contemporary work in quantum information theory has adopted this puppy and used that term enough to keep Google busy. But Axel, you find on Facebook, he does not have a Wikipedia page. You can draw your own conclusions, okay? So I will say no more about Axel, and probably it's not worth mentioning at parties or anything. But I don't think Heisenberg lived alone. He did have a friend. Okay, so we've got Heisenberg, Schrodinger both presenting these theories that seem so distant, and some people were suspecting they were doing the same thing in different languages, different mathematical languages. Some people assumed they were not compatible. And up comes the only mathematician I'll mention tonight, and that's John von Neumann. And von Neumann was working about 8 years later, 1933. We'll see an image of the cover of a book he wrote, but what von Neumann did was to show the absolute equivalence between Schrodinger's theory and Heisenberg's theory. That neither was more encompassing than the other. One could be derived from the other from the one. That's his contribution, plus a very profound formalism for approaching quantum problems, whether you wanted to deal with the continuous wave-like nature as Schrodinger would have it, or the discrete lumpiness as Planck would have it. So there's von Neumann's book. And he wrote this book as Euclid did in dealing with geometry. Euclid put down a handful, tiny number of discrete postulates. If we assume the following things are true, all of geometry follows from it. That's what Euclid did. What von Neumann did was to say this about quantum mechanics. He wrote a postulate about quantum states, what they were, how they looked, how to treat them mathematically, another about how they change. They aren't static objects. It's hard to make them static. They change, and they change in two ways. The third postulate had to do with quantum measurement. And this is a profound movement away from the deterministic Newtonian world. The fact, I mean, if you think like Isaac Newton thought, particles bang against each other, they do things, they move, and if you're gentle enough, you can watch them do it without bothering them. That the observer is not a part of what's being observed. Quantum mechanics threw that out the window and said the observer is as profound a part of an electron experiment as the electron might be. So there was one of these four postulates on quantum measurement. And the last thing, and we'll see all of these kind of in action when we get back to Fliffy, of composite states. If you've got a quantum system, an electron here, perhaps another electron here, and they begin to work in aggregate, how do you deal with that? How do you treat that mathematically? So those are the primary postulates that von Neumann put in his book. Now, I'm pleased to give you something you can Google and not get any hits, and that's von Neumann's duck. I did find a few hits on some subject that a writer thought von Neumann had ducked. So it's not like you'll have nothing to read, but it has nothing to do with Dagmar at all. And again, there'll be nothing more said of von Neumann's duck. Okay, the postulate, von Neumann postulate about quantum states, he was creating mathematical theory, so he had to have some kind of symbolism for quantum states, and there are a lot of pieces of this that we don't need to deal with tonight, but one that I will deal with is called a ket, and it's the right half of a bracket. That's why it's called a ket. And it's a straight vertical line, an angle bracket on the right, and then inside that you put something to describe what it is you're talking about. So, you know, the ket up on that top line is kind of an arbitrary thing that if you can define what you mean by X, then you begin to talk about something that's physical. But you can also use that notation to instead of a symbol or a letter or a number, you can put a picture. And this picture is supposed to represent protons and neutrons in a radioactive nucleus. Okay. Now, my little angle bracket, was kind of lost in translation here, but this is a second ket with the blue arrow representing the fact that an alpha particle has come away from this radioactive nucleus. So we've got a nucleus that can have lots of different properties. We're interested only in two things: the fact that it can decay and the fact that it will decay. So this is the nucleus in its undecayed state, described by a von Neumann ket, and this is in its decayed state, described by of von Neumann ket. What's unusual is the fact that unlike Newtonian science, these things, anything that can be considered a quantum state, can be put into a superposition, so there exists something that is a radioactive nucleus that is at the same time undecayed and decayed, so-called superposition state. So we'll talk about those things. The strange thing about it is that if you happen to come across one of these and look at it, it turns into one of these. And that's kind of the quantum measurement conundrum, that when you get these interesting quantum states, you can't look. Right? There are a lot of fairy tales like that. So von Neumann talked about how these things change. And there are two ways they change. One is if you just leave them alone, they change. Those things transform into something else. So if we started with a quantum state, call it X, and let it evolve unwatched, it can change into state Y or choose not to change into state Y. And you write a superposition this way where the A and the B represent numbers. And those numbers tell you something about what's the likelihood, if you do look, that when you look, you see that. Turns out to be related to A squared. If you look and see that, it relates to the number B squared, and those two probabilities have to add to 1. You're going to see one or the other, but not the combination. The combination truly exists as long as you don't look. The other way things can change is when you look. And here it is. Right? Here's the superposition, but when you look, that little arrow, what happens when you look? You get that probability A squared, that probability B squared. And it seems almost artificial to create these things that you can never see and claim they exist, and yet when you look, they turn into something that you're familiar with. But it's not artificial in that there's an awful lot of results, quantitative results you can get with this assumption that this exists, that are absolutely contradicted if you assume this doesn't exist, it's only this and this. But quantum mechanics works. As weird as it is, it seems to work. Okay, here's an example. We've got a box. We're going to use the box for a cat later. We're going to use it for a radioactive nucleus right now. We put it in the box and we wait. And with the box closed up and not watching, of course it evolves. One half-life later, half-life. Radioactive nucleus, most of them are described by having a half-life. What does that mean? It means if you have a couple of bazillion of these guys, undecayed, and wait one half-life, let's say it's a half-life of 24 hours, wait 24 hours, and look, about half a bazillion of them will be undecayed, the other half will be decayed, half-life. For any one of them, it could decay in a minute, or it could wait for 2 weeks. You cannot predict in any deterministic way when this thing is going to decay, but you can make this statistical prediction about what's going to happen on average. And as far as the one nucleus in the box, if you wait a half-life and open the box and look, you will see this or this, undecayed or decayed, with a probability of 50%. It's all statistical. It is not deterministic. Okay, back to Fliffy. And back to the story of Schrodinger's cat. And it comes from probably not a direct discussion, but a controversy that Einstein carried on for probably the next 25 years. Einstein got one Nobel Prize in physics. In my estimation, he did work that was worthy of at least 3, particularly with the gravitational wave discovery of last fall. That would be his 3rd in my book. But the only one that he was awarded the Nobel Prize for was a quantum explanation. He spent the rest of his career trying to discredit quantum mechanics. He did not believe it. He did not believe that God played dice. He did not believe probabilistic results were the best prediction we could get. There should be a theory that tells you what's going to happen, not what's maybe going to happen. He didn't like it. And Albert, one of the ideas that Einstein presented was, okay, I'll admit that you've got math that will tell you about radioactive nuclei and how they decay. But it cannot have anything to do with macroscopic objects. It has to be just something that coincidentally works for little tiny things. Well, Schrödinger's reply to that challenge was a box. And this represents the inside of the box. He said, okay, let's take our radioactive nucleus and put it in the box, a little chamber here, with a mechanism whereby if the nucleus decays, the alpha particle that's emitted will be detected by this little yellow detector that has a mechanism in it. The mechanism holds up a hammer above a vial of cyanide liquid or something pretty awful. And if the nucleus decays and is detected by this mechanism, the hammer falls and the vial is smashed and the cat changes from this cat to that cat. So that's the Schrödinger's cat story. And he said, basically, to Einstein, the cat is a quantum entity in this story. Before you open the box, you don't know whether you will see a decayed nucleus or an undecayed nucleus. And quantum mechanics says it's this superposition thing. But you also don't know whether you're going to see a live cat or a dead cat. It's this quantum superposition thing. And the cat is as profoundly alive and dead before you open the door to the box as the nucleus is decayed and undecayed. So this is why Schrödinger came up with this story. So here's kind of the quantum mathematics of it. We put the cat in the box. Inside the box we've got the nucleus that's evolving unwatched into part undecayed and part decayed state, and Fliffy, who is evolving into part live kitty cat, part dead kitty cat. Should we look? Well, depends on how you feel about nuclei and cats. Now, there's another notion that came out of this story of Schrödinger having to do with entanglement. Now, this is one of von Neumann's postulates about how do you deal with composite states. Two things that are quantum-like, but how do you deal with them all at once? And for von Neumann, that was pretty easy. Whatever this symbol represents mathematically, you simply take that symbol and multiply it by that symbol. That becomes your complex, coherent state of the two things at once. And if we were trying to describe the Schrödinger's cat experiment using this symbol, we were saying what happens after one half-life of the nucleus is that we get this state, undecayed nucleus, happy cat, and this state, decayed nucleus, dead cat, with equal probability. So whatever A is the same in both cases after one half-life. Composite states behave this way. Entanglement is something that only got taken seriously probably 25, 35 years after Schrödinger's work and von Neumann's work and Heisenberg's work. And that is to have two things that don't have a life of their own. That the life of the cat is profoundly connected to, entangled with the nucleus. And you cannot have in this box a live cat and a decayed nucleus. It ain't going to happen. So let's talk about entanglement in ways that put fewer cats at risk. And in particular, let's think about electrons or atoms. And this blue cat and this orange cat represent two things. Let's say two electrons. And the arrow represents a spin direction. Electrons, most atoms, most nuclei have a behavior that's very similar to that of a spinning top. And it can spin clockwise, it can spin counterclockwise, and they're usually symbolized by an up arrow for one of those two ideas and a down arrow for another. So here we have two unentangled, let's say electrons, both spin up. But if you put these things in your microwave or some quickly varying magnetic field, you can transform that pair of electrons into a superposition state of up, up, and down, down. So you've got two electrons that have exactly the same probability of being found both spin up and both spin down, and absolutely zero probability of being found one up and one down. And that's called entanglement. Neither of these states, just like Fluffy and the nucleus, has a life of its own. They are profoundly entangled. And that brings me to the probably the most modern use of this notion of entanglement, and the most promising use of this, having to do with quantum information theory, and the notion of qubits, Q for quantum, bit for the notion of computer science of bit. Bit stands for binary digit. And you all know that we can send any amount of information using ones and zeros, using things that can have one of two states, classical bits. And sometimes these are magnetic memory, sometimes they're other items, but you can send information with ones and zeros. If those things are electrons, for instance, or atoms, and we're looking at their spins, they become qubits because they have the possibility of becoming entangled with one another. And they have the probability of showing superposition, so that a qubit can be spin up, or spin down, or any linear combination, which means they've got infinite possibility. So the little bit of information you can store on a bit, a yes or a no kind of answer, is paltry compared to what you can store on a qubit, which has, if you can control that qubit enough and control its superposition enough, you can send an infinite amount of information. You can encode War and Peace on a single qubit. The problem with that is that if you have War and Peace on a qubit and look at the qubit, bang, it's gone, right? Bummer. But people have worked hard to try to figure out how to get around that don't look thing. And I'll talk in detail about one of these and then just mention the other, but quantum dense coding, which I'll explain in a bit, quantum teleportation, the beam me up Scotty thing, has been their experiments that have done that with infinitely variable quantum superpositions. Quantum cryptography. Remember, if you look, it changes. You can send encrypted messages, and if somebody eavesdrops, they've looked at it. And the message arrives altered, and you know it's been looked at, so you can send it again. So the notion of quantum cryptography is much better. There's actually quantum entanglement clocks, and there's a lot of time spent now in quantum computing. But let's talk about dense coding, and allow me to read a little story about Della and Jim. Della and Jim are young, poor, and in love. And alas, Jim must soon depart for a far-away land. The trip is hard and dangerous, the return trip ever more so. Jim tells Della that whether he even attempts to return will depend on the answer to two questions, answers which she must send him by year's end. Question 1, did the Cubs win the World Series? Question 2, did the Democrats win the presidential election? On his last visit to Della before his departure, Jim arrives distraught and disheveled. He has just come from the shops where he pawned his most precious and only valuable possession, a gold watch. With the proceeds, he has purchased 2 qubits for Della to use to send him the answers to his questions. But he had so little money left, he could only buy a prepaid card enabling her to send 1. Not knowing the answer to both questions, he cannot return. Woe, says Jim, is me. Della ponders. She could manipulate one qubit to be an up or a down, send it to Jim, and he could determine its orientation. If they've agreed that up means yes and down no, she could inform him of the cub's ultimate fate. But if she can send only one qubit, how can she convey both answers? Seeking a resolution, Della takes the qubits, rushes out the door towards the shops, her beautiful long hair, pay attention, long hair flowing behind her. Entering a wig maker's shop, she emerges almost at once, fleeced as well as shorn, clutching a modest fistful of coins. Standing dejectedly by the curb, grasping the two qubits and the meager compensation, she's approached by a strange man with an even stranger cat. "May I be of assistance?" he offers. "If only," sobs Della, and tells the man of her predicament. "This is your lucky day," he says, relieving Della of her qubits and, of course, her money. The qubits he puts into a small crate. The cat follows, and the crate door is closed. Soon he opens the crate. The cat emerges. He reaches in to remove two tiny, cheap lockets. "This is what you need," he assures Della, handing her the lockets. "Thanks to my cat, Fluffy, the qubits have been entangled, and one is within each locket." Quickly moving to open a locket, Della's hand is restrained. "You must never look," she is told, "but I must be sure you're at least giving me back my qubits. Do not doubt. You can trust me. I'm a physicist." That wasn't supposed to be a laugh line. This is what he told her to do. Two lockets, a qubit in each, locked away so you neither can look at them. And it's an entangled pair that I will describe by that symbol. And when Jim departs, he takes his with him, she keeps hers. The notion of entanglement does not diminish with distance. So he can go to darkest Peru if he chooses, and the two qubits are still as entangled as they were when they were side by side. Della, by December, knowing the answer to both of the questions that Jim needs to know, works on her qubit alone. She has a microwave oven. Okay. Puts it in there. They are entangled qubits, so as she changes hers, his changes. This is what Einstein referred to as spooky action at a distance. He didn't like it. Right. But the experiment has shown that this happens. This entangled pair, as she alters hers, his is altered. And because there are two qubits, there are four distinct states. If you think of even if you look at them, if you think of the classical notion of two bits, up, 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 down, up, and down, down. Four distinct states. And she can change the entangled pair that the two have in their lockets into any one of these four states. Then she uses her prepaid card, sends her single qubit to Jim. He then has both. He can measure the pair, and he can find one of four answers. Yes, yes. Yes, no. No, yes. No, no. He knows what he needs to know to decide whether it's worth coming home. Okay. That's quantum dense coding. This is the simplest example where you can send a single bit and convey 2 bits of information. And this is easily magnified into sending many more than 2 times the amount of information that you could classically send by conveying qubits instead of bits. So back to the notion of quantum information theory and these things, that's this quantum dense coding. Quantum teleportation, very briefly, is the notion of sending a quantum entity, a qubit, in a superposition state, so it has this infinite variety. You can transport that with total fidelity over a distance as long as the sender and the receiver share an entangled pair of qubits. So the sender entangles the unknown with, let's say, her qubit, and then at the other end, Jim can measure, and his particle, and yet the single state that he had is transformed into this unknown state. So you can do teleportation with electrons, presumably with cats, presumably with starship captains. I've talked a little bit about cryptography and about how you can know if somebody's cheating and looking at what you're sending because it changes the answer. Quantum timekeeping is interesting. Right now the time standard is a clock, atomic clock, that loses about 1 second or has a variability of 1 second in 300 million years. A million years ago, beetles were showing up on the planet, the first beetles. And if these, not the other ones. If these, the first two beetles that emerged had watches of that sort, their watches would still agree right now to within a second. There is, however, an entanglement clock that, were it built, would keep time, lose 1 second in 15 billion years. Interesting number of years. That's the age of the universe. That's how long ago the Big Bang happened. And it's probably not worth getting any better than that. And then quantum computing, there's a lot of work being done in quantum computing, and one of the most profound pieces of things that has been proven in principle is the fact that using quantum computing you can factor large integers. Why is that important? Most of the bank encryption that are keeping our accounts safe worldwide is based on the fact that factoring large integers is something that would take hundreds, if not thousands of years for a regular digital computer to do. A quantum computer could do it in a matter of seconds. So it would totally disrupt that kind of encryption if we had that. So that's, I think, enough of me. I do want to assure Emily and anyone else in the audience who's worried about these cats that they all came home the very same day. Thank you.